Okay, welcome back. This is Spin Dynamics, term 3. We are starting an exploration of various advanced topics, such as approximations, relaxation theories in their various formulations, then stochastic Liouville equation, and things like that. So what we will be looking at in this lecture is the very start of it, namely the secular approximation and the fact that quite a few spin dynamics simulations needn't actually be carried out in the full form, as it were, for the Hamiltonian, and significant simplifications can be made if we take a look at which interactions are actually important and cleverly get rid of other interactions. So if we have a spin system, let's say an NMR spin system, its Hamiltonian would have several classes of terms. It will have the Zeeman splittings, so omega L, Lz, for example, something that comes from the main magnet field and has the order, let's say, of 1 gigahertz. So quite a fast oscillation, really on the time scale of typical NMR experiments. So we would normally run our FID for between 0.1 and 1 second, so gigahertz. And it will have things like couplings, so let's say dipolar coupling, that would have an amplitude of around 1 kilohertz, so maybe 10 kilohertz or so if it's between protons. Then it will have the J couplings, which have the order of hertz, and maybe some other things. So in a typical NMR problem, therefore, we have a fairly dramatic separation of timescales. The primary Zeeman splitting goes at 1 gigahertz, whereas the nearest coupling and the nearest offset from resonance, if we're looking at chemical shielding, is of the order of kilohertz and tens of kilohertz. So there are quite a few orders of magnitude between these. What's also important is when we start propagating our system in time, so we're looking at things like that, exponential minus I, H, superoperator, delta t, let's say, acting on some initial state ρ0 in Liouville space. In order to correctly reproduce this gigahertz dynamics, it will have some sinusoids, and those sinusoids will have several lobes per nanosecond. In order to sample them faithfully, we need at least 2 points per period, as a Larmor condition. But what that necessitates is very fine sampling. So we'll have to take very small delta t's. As a matter of fact, the optimal delta t is of the order of 1 over the norm of the Hamiltonian, and the norm is the biggest eigenvalue, and if we've got the eigenvalues of the order of gigahertz, and if we've got 10 spins, the collective 10 spin coherences might evolve as fast as 10 gigahertz, this will be a very small number. Result being that we would have to make the simulation go forward with very, very fine time step, and if we're running it for a second, that means 1 billion points. Clearly, well, some computers can do it, but it would really be good if we could avoid propagating at the gigahertz rate and can actually propagate at the rate of the interactions that actually matter. And it turns out there exists an approximation to this effect that can actually accomplish it, and it is called the secular approximation. Right. We considered rotating frame before as an interaction representation, and I will now remind you what it is and how it comes about. So we have our Liouville von Neumann's equation. We've got d by dt of our rho state vector, and that would be minus I h0 plus h1, where I will tell you in a moment what 0 and 1 means, and then our rho. Here I have partitioned our Hamiltonian into terms of different magnitudes. I have partitioned it into terms which are large, but also importantly simple, like the Zeeman interaction, and these terms are small and complicated. Let's say dipolar interaction or J coupling or things like that. So we would ideally like to get rid of the large and simple term and preserves the small and complicated one so that we can actually gain information from our simulation. And well, we know that standard exponentials and blah 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 accomplish this propagation. But what we'll now do is something that will at first look like I'm pulling rabbits out of the hat, but then we will resubstitute the result into the original equation and see that it actually works. What I will do is the following. I will define sigma of t to be this. It will be E I H0 double hat T rho T. So I will define a different density matrix, which will be the original density matrix multiplied by the propagator, but only with respect to the H0. I will also define H1 double hat R, and R refers to the rotating frame, and I will explain why rotating in a moment, of t, originally it was time independent, would be this E I H0 double hat T H1 double hat E minus I H0 T. I'll just drop the double hats so that I don't actually have to write them all the time. So a fairly strange transformation to make, clearly an obvious one. So why don't we substitute the result back to where it came from and see what happens. Now clearly the inverse of this would be rho of t equals to E minus I H0 t sigma t, and then H1 t would be E minus I H0 t H1 R t E plus I H0 t. And H1 in our case doesn't actually depend on time. So let's plug it back and see what happens. Then d by dt of that, so d by dt of E minus I H0 t sigma t will be equal to minus I H0 plus H1 E minus I H0 t H1 R t E plus I H0 t acting on rho, that is minus I H0 t sigma t. Well, one thing cancels immediately, yeah? This exponential goes away. And we can also open the bracket here on the derivative. Just a standard product rule. It will be minus I H0 E minus I H0 t sigma t plus E minus I H0 t d by dt sigma t. And that will be equal to this. Well, let's see what we've got. We've got minus I H0 E minus I H0 t sigma t here, and here minus I H0 E minus I H0 t sigma t here. So this term disappears as well, and it cancels with this one. Furthermore, we've got E minus I H0 t here and E minus I H0 t there, so this disappears as well. So what we're left with as the result of this is d by dt sigma t is H1 R t sigma t. Dramatic simplification, see? At least in nominal terms, yeah? Pure letters. So returning to our multi-hat notation. So that's an operator, that's an operator, and this is a commutation superoperator. So you see what happened. Nominally, at least, H0 has disappeared from the equation. Now this happened at the cost of acquiring a time dependence for the Hamiltonian, but at least formally H0 is gone. Now, what accomplished the transformation was this particular move. We multiplied our density matrix by this interesting thing, and this is known in the trade, when it is done with respect to the Zeeman Hamiltonian, this is known in the trade as the rotating frame approximation. And it's not immediately obvious why that should be so, but it becomes obvious if we look at what this thing actually is, in the case where H0 is the Zeeman interaction. And in the case where H0 is the Zeeman interaction, that is minus I z h, so that would be omega L z t. That would be the exponential. And I don't know how many of you remember the SO3 lecture when we dealt with the rotation group. We found that a rotation is in fact accomplished by such an operator, minus I L Z alpha, where alpha is the angle of rotation, and that was a rotation around the z-axis. So you see what happens. We are having, this is a super operator, but it's acting on operators, so just a joint representation. We are in a way rotating something, and we are rotating it, its position is depending on time, so it's a time-dependent rotation. And in very, very simple cases, where we just have one spin and we treat it classically, this entire transformation does indeed amount to rotating the frame of reference, and then working in the rotating frame. But you can see in full generality, when we don't look at any specific simplified models, but we look at actual Hamiltonians, this is also possible, and this particular transformation accomplishes that. So, okay, we now defined something that is in magnetic resonance language known as rotating frame transformation, but in a more general quantum mechanical language is known as interaction representation. So this H0 is known as the background Hamiltonian, and the H1 is the interaction Hamiltonian, and then a transformation that removes the background Hamiltonian and only focuses on the interaction one is unsurprisingly known as the interaction representation transformation. So, okay, we got it. Let us now see what we can actually do with it. It turns out quite a lot, and it turns out that one of the consequences of what we're doing will be our ability to actually ignore this H0 term when we're simulating our spin systems, and it is known in the trade as the rotating frame approximation. So let us now take a slightly closer look at what this transformation does to our Hamiltonian. So I will erase most of it. I will erase the sigma definition here, it's not necessary, but I will focus on this particular transformation here. So, let's say our H0 is the Zeeman interaction. So, in a two-spin system, say, so two spins, we will have H0 will be omega L L Z plus omega S S Z operators. And for a single spin, it will just be omega L L Z. Right. And what have we got here in the H1? Well, the most complicated H1 possible would look like that. H1 will be. It will contain possibly the offsets here. Spins are shielded to a different extent, and they will have offsets from the magnet frequency. So one thing that it will have is offset terms. So let's see, omega 1 L Z plus omega 2 S Z. So the offset terms for spin L and spin S. What will also be there is some kind of J coupling. So plus pi J Lx Sx plus Ly Sy plus Lz Sz. Isotropic coupling, and as we know from the previous lectures, there will also be an isotropic coupling. Dipolar, quadrupolar, whatever it is. So we will have further terms here, and in a two-spin case, let's just write out the irreducible spherical tensor expansion for whatever couple we've got. M from -2 to 2, A, M, T, 2, M, two-spin irreducible spherical tensor. And these operators all together are the most general possible coupling Hamiltonian between the two spins. So offsets, scalar coupling, isotropic coupling, anisotropic coupling. Nothing else can be there between just two spins. So, well, let's take a look how this behaves under the rotating frame transformation. So what we will be rotating with respect to is this. And ultimately, because these things are expressible in terms of commutators, we need to compute a few basic fundamental commutators. Right, what I think I'll do before we do that is look at the transformation of just the Hamiltonian. So, not the double hat everywhere, but just the hat, because really the adjoint can be taken afterwards. It doesn't matter whether we're doing it in the direct representation or the adjoint representation. Those are both faithful representations. So, for simplicity, what I'll do is just consider the operators themselves. Well, what we can immediately observe, of course, are simple things, like the fact that Lz commutes with Lz. That is definitely 0, yeah? You can either check it with differential operators, or you can check it with matrix representations, doesn't really matter. This is definitely 0. The other thing, slightly less obvious, I guess, but that is also 0, is this. Lz plus Sz commutes with the scalar coupling. So Lx Sx plus Ly Sy plus Lz Sz. That is also 0. Slightly harder to prove, but I'll just leave it as a homework exercise. There's nothing complicated. It clearly commutes with the last term, and these terms you can express in terms of raising and lowering operators. And then you know how raising and lowering commutes with that from the commutation relations that we have derived in the lecture where we introduced spin. Right, what's particularly important, however, is these irreducible spherical tensors, because of their group theoretical heritage, actually happen to commute rather well with Lz. In particular, what's known about them is Lz commutator with TLM, where this is a single spin operator, just returns the projection, so M, T, LM, so it's an eigen operator of that commutation. And if we have a two-spin operator, it commutes in that exact way with the sum, plus Sz, T, M, Ls, so two-spin irreducible spherical tensor, returns the projection quantum number and that same irreducible spherical tensor. So, with these commutation relations in place, we can actually evaluate the result of this action. And what I will now do is assume that the spins are in fact of the same species. That is, in order to take advantage of this commutation relation and that commutation relation, we will just say that this is omega, so the carrier frequencies, let's say these are two protons, are both 600 megahertz in a 14 Tesla magnet, so we actually have Lz plus Sz. And I will leave that restriction later on, because it turns out that the case where they are different is actually a lot simpler than the case when they are the same. So I will first treat them as if they were the same, and then I will treat separately as a considerably easier case when they're different, because we'll be able to ignore a few more things when they're different. So with these commutation relations in place, let us proceed to calculate these commutators for the various parts of that Hamiltonian. Now, where shall I make myself some place? I think I should wipe the board. It's rather big story. Well, you've got all those commutators in your handouts. So just refer to them, and I need as much of this board as I can get hold of. Let's take a look at what that is. So E I omega L Z T, then irreducible spherical tensor, TLM, let's say a single spin one, and then E minus I omega L Z T. Double commutator. We have shown in term 1, I think, when we introduced the joint representation, is that this is in fact equal to x minus, or in this case plus, I omega L double hat Z T acting on T L M of L. Now that is, of course, a Taylor series, n equals 0 to infinity, I omega T power n over n factorial, L Z double hat power n T L M L. This is an n-fold nested commutator, and we know what a commutator with LZ is equal to. It's MTLM, so simply m pops out n times in front of it, and the operator vanishes. We call it a sum, and from 0 to infinity, I omega m t to the power n over n factorial T L M of L, and this is just a scalar exponential, so that becomes equal to x I omega m t T L M L. So you see what happens is when we apply the rotating frame approximation, the irreducible spherical tensor operators acquire an oscillating multiplier. And this multiplier oscillates very fast indeed. It oscillates at the carrier frequency of the vector. So whatever happens to the dynamics, therefore, will fall quite sharply into two categories. There will be terms in the rotating frame Hamiltonian which will be time independent. So for example, the case where m equals 0, this term will just vanish. And there will be terms which are oscillating at a colossal frequency. Let's write them out explicitly. So for our Hamiltonian now, so H1 rotating frame of T, what I will do is I'll take that entire big Hamiltonian that we looked at, the biggest possible, the most sophisticated possible Hamiltonian for the coupling of two spins, and I will transform everything and take a look at what happens. So our offsets commute with the operation, so they remain unchanged, omega 1 Lz plus omega 2 Sz. J coupling commutes with the operation, and so it remains unchanged. So phi J L S vector operators. I just should note that if we have a two-spin irreducible spherical tensor and a two-spin rotating frame transformation, then the result is of course identical, because we commute in an identical way. Then what we've got is here is just one term that yields 0 in here, so that would be A0 T2 0 Ls, and these are the time independent parts. And now we'll have a few time dependent ones. We'll have the remaining sum, this time over m unequal to 0, A m E I omega m t t to m Ls. So this is the rotating frame expression for our coupling Hamiltonian. So there are things which are static, and there are things which oscillate at a gigahertz frequency. So the secular approximation now is, you can probably guess what that is. Interestingly, it dates back to Johannes Kepler, who did it in the case of astronomical bodies. But in our case, what we will simply do is say that on our scale, the gigahertz dynamics is irrelevant because it averages out very quickly relative to all the other interactions which are static. And this is secular approximation. And that is known as the secular coupling Hamiltonian. And it's used rather a lot. Now, you see what happened. We have simplified our problem enormously in terms of what kind of magnitudes we have in the Hamiltonian. This is of the order of 10 kilohertz. Here, what's the biggest proton offset out there? This is just a few hertz, really. This, if it comes from proton dipolar interaction, is here just 10 or 20 kilohertz, depending on the distance. So we have cut out at least 4 orders of magnitude in the resulting dynamics. And so what we can now do, instead of taking a nanosecond time step, we can actually take a fairly leisurely sub-millisecond time step, and doing 10,000 steps for an FID is already something sensible. It's the Larmor condition anyway for the kind of frequencies that we realistically encounter in NMR spectroscopy. So, and that is the background to that approximation that we have there. Right. Now, let us say these are no longer protons. So in the case of protons, that's the end of story. This is the Hamiltonian we've got to deal with, and there it is. Now, let us say these are no longer two protons, but these are now a proton and a carbon, say, or a proton and nitrogen, or a carbon and nitrogen, so different species. As well as the approximations that we've just made with respect to the carrier frequency will be somewhere in the middle. So let's say if one is proton, the other is carbon. Proton 600, carbon 140 megahertz. So let's say the middle will be somewhere around 300 or 400. So that would still work, all of it. But in the case of carbon and proton, the difference between omega 1 and omega 2 would no longer be 10 kilohertz. It will also be several hundred megahertz. So why don't we do another rotating frame approximation, or equivalently another interaction presentation transformation, with respect to this frequency difference. So we can just nest these things and put another pair of exponentials around it, but with respect to this parameter and the difference of it, which is now large. And then hopefully we can neglect something else, because there will also be rapidly oscillating terms, and there will be terms that do not depend on that particular transformation, stay invariant, and therefore stay time independent. And for that, what I need to do is to write out this term in slightly more detail, in particular to write out this irreducible spherical tensor operator explicitly in terms of what it contains. What I will also do is translate LXSX and LYSY into raising and lowering operator, because those are ordered under the commutation operations that we are about to carry out. So, having done all of that, so you have all of that in your handout, just using the definitions for all the necessary operators, regrouping them, collecting the terms. This is not a linear algebra class. I will just write out the final result, and you've got all those details in your handout. So then the new H0, the one we are taking the second rotating frame approximation with respect to, will be our omega 1 LZ plus omega 2 SZ. So these big ones. And the new H1 will be the remaining, and if I open up all the notation and collect the terms, that would be root 2 over 3 A0 plus pi j multiplied by LZ SZ. And you can see what's going to survive here. LZ SZ commutes with both, so this will stay time invariant, plus the rest of those terms. That will be pi j over 2 minus water root 2 thirds A0, the 0 quantum term, L plus S minus plus L minus S plus. And well, this commutes with their sum, but doesn't commute with it when the coefficients are different. So this will acquire time dependent, and, well, at this stage, hopefully cancel. So let us apply the second transformation, and I will just write out a couple of Hamiltonians. Together with the Hamiltonians that we've already saw how they commute, there are a few more in your handout. So for example, Lz commutator with L plus S minus is just given by its commutator with L plus, because this is identity on the S spin. So what we'll have is just L plus S minus. And similarly, if we've got Lz commuting with L minus S plus, what we will have is minus L minus S plus. And so on. For the rest of them, I have given you the table in the handout. I have given you the corresponding translation into the exponential operators. So to cut a rather long story short, what we've got at the very end of it is this. In brackets here, we've got E I omega 1 minus omega 2 T L plus S minus plus E minus I omega 1 minus omega 2 L minus S plus. See, if we had these two frequencies belonging to protons, this wouldn't have been a large frequency at all. This would have been a couple of kilohertz, and we would not have been able to ignore it, because our couplings, other couplings also happen on a similar scale. But if they're carbon and proton, this is a few hundred megahertz, and so this entire term can also be ignored. And this also has a name, whereas the previous coupling Hamiltonian was called secular coupling. The coupling in this case is known as weak coupling. And you have, of course, seen both in your usual magnetic resonance course. If we have the case of a secular coupling between two protons, it alters the intensity somewhat, and we've got things like that. Yeah, so the roofing pattern, and the zero quantum terms are in fact responsible for this incline. But if we've got spins which are dissimilar, we just have the weak coupling, and they split into elements with equal intensity, because Lz and Sz term doesn't actually alter the intensities of the transitions, it simply just splits them. Right, so that's secular coupling for homonuclear systems and weak coupling for heteronuclear systems, or in greater generality for every case where the frequencies in question happen to be related as we had assumed them to be related in this case. Now, the last topic for today is something that we really only ever encounter in electron spin resonance, but many of you are EPR spectroscopists, and that's important. That's known as the pseudo secular. And that is the case where the frequency of one spin is massively greater than the coupling. And you can guess what that spin is. It's usually the electron, but the frequency of the other spin, this nucleus, is in fact comparable to the couplings. So let's say we're doing X-band ESR, and we look at the electron, and it's of course those 9 gigahertz, and it's massively greater than any hyperfine coupling, which is usually sort of 20 megahertz or so. But if we look at the nuclear frequency, the proton frequency at the same field is also, I think it's 19 megahertz or something, so it's comparable to the coupling. So we can certainly make a secular approximation with respect to the electron, but we cannot possibly make a secular approximation with respect to the nucleus. And this partial secular approximation, the one-sided secular approximation, gives rise to fairly specific collection of terms in the coupling, which are known as pseudo-secular coupling terms. And they are following. So let's say we've got our Hamiltonian. So what we have in the case of EPR, I'm running out of my marker here, is omega E, so the electron Larmor frequency, Lz, plus omega n, the nuclear Larmor frequency, times Sz plus the isotropic hyperfine coupling, so Lx Sx plus Ly Sy plus Lz Sz, plus the spherical tensor expansion of the anisotropic part of the hyperfine coupling, m from -2 to 2, b m t to m ls. Right. Well, we can expand this, and after we open up all the terms and after we move x and y into plus and minus, what we've got is the following. We've got omega e Lz plus omega n s z plus a over 2 L plus s minus plus L minus s plus b minus 2 L minus s minus plus b2 b minus 2 over 2 b2 over 2 L plus s plus minus b1 over 2, I'm just writing out all the terms explicitly, Lz s plus L plus s z plus b1 over 2 b minus 1 over 2 Lz s minus plus L minus s z, and finally the b0 term plus b0 and t to 0 irreducible spherical tensor, 2/3 Lz s z minus quarter L plus s minus plus L minus s plus. Okay, so let's take a careful look at these terms and see which ones are going to acquire a frequency if we do a rotating frame transformation with respect to omega e Lz. So clearly anything with L plus and L minus will get a frequency. So that would be this, 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 that, but not this. See, Lz, Lz, L minus here, then this will survive, this won't, and that won't. So if we go through all the necessary wrapping with exponentials, acquiring the frequencies and so on, and so after we do that and write out the surviving terms here, what we get is the following. We get H1R containing omega n s z, so we haven't made any rotating frame approximation with respect to the nucleus, plus A L Z S Z, so just the weak type, weak remaining part of the hyperfine coupling, but we will also have the following terms, but minus B1 over 2 LZS plus B minus 1 over 2 LZS minus plus B naught groups 2/3 LZSZ. So we can group A with this, and we should also make an observation that this operator isn't Hermitian, and that operator isn't Hermitian, and their linear combination is only Hermitian if B1 is equal to B minus 1. And if you look at the matrix itself, that is in fact a requirement that's imposed by it being a symmetric matrix, which it always is. And so after we make that particular assumption and write out the final Hamiltonian, what we've got is omega n s z plus the bracket b naught root 2/3 plus a l z s z. So this is the sort of weak coupling that we just saw for different nuclear spins, but in the electron case we also have the remaining part b minus 1 l z s x, where x came out of the fact that b1 was minus b minus 1 in that case, and the plus and the minus combine to get us the x. So this is the nuclear Zeeman term. This is the isotropic hyperfine weak part of it, and this became known in the trade as the pseudo secular term. It is secular with respect to the electron, but it's non-secular with respect to the nucleus, and it is very often this term that in fact dominates and determines the dynamics of various complicated experiments such as endorecine and DNP. So if you are EPR spectroscopists, you will certainly encounter this thing on quite a few occasions. So, okay, to give you a summary, I put the table in the handout. So, if we are in a low field, that is, every frequency in the system, including the Zeeman frequency, is comparable to the coupling, then tough luck. No such approximation is ever possible. So, in low field, we will have to propagate at the full magnet frequency, no matter what. However, things are rarely that dramatically bad. We usually work in high field because it gives us resolution. So in high field, if you have a homonuclear system, then you can get away with the secular Hamiltonian. If you have a heteronuclear system, you can get away with the weak coupling Hamiltonian. And if you have an EPR system, you will likely get away with the pseudo secular approximation. So, simple summary, there in your table, low field, nothing. High field homonuclear secular coupling, high field heteronuclear weak coupling, high field EPR pseudo secular coupling. So please remember that it will save you a considerable amount of headache in trying to track these terms. And important to understand these terms as well, because quite a few textbooks and papers launch into this straight away without really explaining where it came from, and today's derivation hopefully gives you background as to where it all came from. Okay, that's it for today, and relaxation theory from the next lecture.